Okay, so we've seen now the product rule, which gives you a method that you can use to differentiate functions which appear in the form of a product. Now we're going to talk about the quotient rule, which tells you how to differentiate functions that appear as a fraction. So this time I'm not going to prove this one to you in detail. I'm just going to give you the rule, and here it is. So if you want to take the derivative with respect to x of a function that appears in the following form as a fraction, f of x divided by g of x, well, then you do the following. And it starts off a little bit like the product rule. We're going to have two terms in the numerator which are exactly the same two terms that you see in the product rule, f prime g of x and f of x g prime of x. But there's two differences. The first thing is we're going to subtract instead of add. So it's not like the product rule in that way. In the product rule, you added instead of subtracted here. But there's one other difference too. We're also going to have a denominator of this fraction, and it's going to be the square of whatever the denominator was in your original function. So you're going to divide by the square of this function. So that is the quotient rule. And if you want to see why this is true, you can use the approach that we used to prove the product rule. You can just define a new function, capital F, and define it by capital F of x is equal to f of x, little f of x divided by g of x, set it to be equal to what's inside here, the square brackets, and then apply the limit definition of the derivative to that new function. And if you carefully follow a similar approach and use the same trick actually as we did on the first page of this section to prove the product rule, everything just works out and you end up getting this rule. So I'll leave it to you to check that as an exercise if you're interested, but I'm not going to cover it now. It's one long proof is enough for this section. So, but let's look at how to use this rule. So we've got two examples here. We want to differentiate these two functions, and they both appear as fractions. So you can see these are good candidates for the quotient rule. So let's start with part A. So we've got our function capital G of x, and we want to differentiate it. So we're going to calculate capital G prime of x. So let's apply the quotient rule carefully. So the first thing we're going to do is write down this term where we differentiate the numerator, but we leave the denominator alone. So we're going to differentiate x squared minus 2, and then we'll multiply it by 2x plus 1. Okay, so that's this first term of the numerator. Then we're going to subtract this next term where we leave the numerator alone, but we differentiate the denominator. So we're going to get x squared minus 2 times the derivative of 2x plus 1. And then all of that is going to be divided by the original denominator squared, right? We're going to divide by the square of 2x plus 1. Okay, so now what's next? Well, we have to take these smaller derivatives, right? X squared minus 2 and 2x plus 1, we have to differentiate both of those functions. But that's certainly easier now than differentiating the entire capital G function, right? So that's how the quotient rule really takes a more complicated derivative and turns it into smaller derivatives, little f prime of x and little g prime of x, and the rest doesn't involve calculus, right? This occurrence of the denominator, g of x, and then you have an f of x that occurs here, and then g of x squared. None of those functions have to be differentiated. It's just these pieces here that need to be differentiated. Okay, so, well, what do we get? Well, the derivative of x squared minus 2, well, derivative of 2 is 0, so it's really just x squared. So you use the power rule on that, and you're going to get 2x. So you can actually fit this here. We're going to have 2x times 2x plus 1. And then what will we have over here? We'll have minus, and then x squared minus 2 multiplied by the derivative of 2x plus 1. We'll start with the derivative. Derivative of 1 is 0, and derivative of 2x, well, that'll just be 2. So this entire derivative is going to evaluate to 2. So we're going to have 2 times this factor here. So we can say minus 2 times x squared minus 2. All that is over 2x plus 1 all squared. Okay, well, now what? Should we stop? We could. I mean, this is technically the derivative, right? There's no derivatives left in this expression. This is all just an algebraic expression now, so this really is g prime of x. But there's something unsatisfying about it, because the numerator is not factored. Not completely anyway, like this part here is factored, and this part here is factored, but the entire numerator itself is not factored, and it's not expanded either. So why don't we do this? How about we expand, we multiply the 2x into the brackets, and we multiply this 2 into those brackets, we'll expand everything out, and then we'll combine like terms, and see if anything factors nicely after that. Because sometimes what'll happen is it'll just collapse down into nothing afterwards, and then it would be a missed opportunity not to recognize that. So let's do that. In our next step, we'll expand the brackets. This is just, everything after this stage is now simplification. The derivative part, the calculus is over, really, for this question. But let's expand this out. So we'll get 4x squared plus 2x. And then over here, we're going to have minus 2x squared plus 4, right? Minus 2 times minus 2. And then our denominator will be 2x plus 1 all squared. And then what happens if we combine like terms now? We have 4x squared minus 2x squared. Well, that's going to give us 2x squared. There's a 2x term, so we have plus 2x. And then we have our constant term of plus 4. And it looks like we can do a tiny bit of factoring. We can factor out a 2. That's going to give us 2 times x squared plus x plus 2 on the numerator. And then you could say, okay, well, what about the quadratic? X squared plus x plus 2. Does that factor even further? Maybe that factors. And it's worth asking that question, but it turns out the answer is no. You're not going to be able to factor that anymore. So this is as far as you can go with that one. So this is about as good as it gets. Okay, so that's part A. Let's look at part B now. Part B is actually a little trickier. So we've got our function y. It's a function of t. So y is a function of t, and here's our numerator, t cubed plus 3t, and our denominator is t squared minus 4t plus 3. So what happens if we plug this into the quotient rule? Well, the first step, if we just write out the quotient rule, we'll say that y prime is, well, let's check the pattern, right? Differentiate the numerator, leave the denominator alone. So let's start with that. We're going to have t cubed differentiated, or t cubed plus 3t, I mean. That's our numerator. That's going to be differentiated, so let's write that down. But then we're going to multiply by t squared minus 4t plus 3, unchanged. So that is this term here. But then we need to form this term after and subtract it. So now what we're going to subtract from that is t cubed plus 3t. So the numerator unchanged now, multiplied by the denominator differentiated. So that is our numerator, right? So we got the top two terms. But now we need to divide by the square of the denominator. So the denominator, I know I'm sliding around, sorry, I'll try to minimize that. We got the t squared minus 4t plus 3, that's our denominator. We're going to have to include that on the bottom with a power of 2. And that's the step where you write out the quotient rule. And now from here on, it's just evaluating these smaller pieces here, right? So let's do that. Okay, so the first one, we can do the power rule on t cubed and differentiate 3t in a similar manner. We've seen expressions like this before. If you have a constant times a variable and you're just differentiating with respect to that variable, the result is just going to be the constant. So the derivative of 3t is just going to be 3, and the derivative of t cubed is going to be 3t squared. So we'll have 3t squared plus 3 multiplied by t squared minus 4t plus 3. So that's the first term, just turns into this. Over here we'll have minus t cubed plus 3t, and then we'll have to differentiate this quadratic over here. So t squared, differentiate that, and you're going to get 2t. If you differentiate the minus 4t, you're going to get minus 4. And then if you differentiate 3, it's a constant. So it'll be 0, right? So we can close our brackets there. Okay, so that is our numerator now. And our denominator is t squared minus 4t plus 3 all squared. So now, again, we're in the situation where the calculus is done. We've finished taking all the derivatives, but our numerator is just absolutely awful to try to wrap your head around because it looks like it's factored. A naive person might look at this and say, oh, look, this is great. This is factored over here, and this is factored over here. But that subtraction between them throws it all out the window. The numerator is not factored at all. Parts of it are factored over here, and parts of it are factored over here. But as a whole, the numerator is not factored. In fact, it's as far away as it could be from being factored, because if you were going to try to factor it, you'd probably have to start by expanding everything out and collecting like terms. So that's what we'll start by doing. Let's just expand and collect like terms just like we did last time. Maybe things will simplify, maybe they won't, but that's a good idea to get in that habit of checking. Okay, so let's expand the numerator. So first we'll expand these brackets. So I'll start by just multiplying each of these three terms by 3t squared. So 3t squared times t squared is going to be 3t to the 4. 3t squared times negative 4t, that's going to be negative 12t cubed. And then 3t squared times positive 3 is going to be 9t squared. And then now we'll multiply each of these three terms in these brackets by the number 3. So we'll have plus 3t squared minus 12t, going 3 times negative 4t, and then 3 times 3 here is going to be 9. So that's quite a few terms, but that's because we were foiling out brackets, and this one had 3 terms in it. Now let's expand these brackets out. So I'll put a minus and then a square bracket just to make sure I don't make any sign errors because of this subtraction here. So t cubed times 2t, that's going to be 2t to the 4. T cubed times negative 4 is going to be minus 4t cubed. Then we have 3t times 2t. It's going to be 6t squared. And then 3t times negative 4 is going to be minus 12t. Okay, and all of this is still divided by the same denominator, t squared minus 4t plus 3 all squared. Okay, so now let's clean this up. Now, if you're careful, we can do this all in one go. But here's the trick. We don't want to just look around and start randomly grabbing terms and making observations here or there and then writing all over this, crossing stuff out. It's just too easy to get lost and forget and lose your train of thought and forget what you're doing. So the best way to do this, we can do this in one more step if you do it the way I suggest, which is just look at one power at a time. So what I mean by that is look at the t to the 4 terms. Only consider t to the 4 terms. Where are they? There's 3t to the 4. Where are the rest? There's one here, 2t to the 4, but it's inside of a subtraction. And then that's it, right? So there's just 3t to the 4 minus 2t to the 4. Well, that's going to give us 1t to the 4. And now we're done with the t to the 4 terms. Forget about them now. So now we'll go to the t cubed terms. Let's look for them. We've got negative 12t cubed. Any other ones? Oh, there's one right here. Negative 4t cubed. Except it's inside of a subtraction. So it's actually going to be positive 4t cubed. And that's it for t cubed terms. So we've got negative 12t cubed plus 4t cubed. We're actually going to have negative 8t cubed. And now we're done with the t cubed terms. Now let's look for t squared terms. What do we have? Go through, well, we got 9t squared plus 3t squared. So this is 12t squared here. What else do we have? If we move forward, looks like this is the only other one, 6t squared. But it's inside of a subtraction. So we've got 12t squared minus 6t squared. We're going to have 6t squared left over. And then now we just have the constant terms. So where is, or not the constant term, sorry, the linear term, the power multiples of t. So we've got one here, negative 12t, and then what else? Negative 12t again, but this one's inside of a subtraction, so this is plus 12t. So we've got negative 12t plus 12t, those are going to cancel. So the t terms actually cancel out, and we don't have to worry about them. So the t terms are done now. And the only thing left is the constant term, and there's only one constant term of 9. So we can say plus 9, and that's our numerator. Okay, so if you do it that way, you can take your time and do it slowly, and you can do it in a single step. But don't be tempted to rush there, because it's easy to make a mistake. Okay. Alternatively, you could take a step to distribute this negative into the brackets, change the sign of all of these terms, and then you could slowly work your way down that way as well. That's another option. Okay, so that is your derivative of y. So that finishes this example. Okay, so those are two examples of the quotient rule.